The Earth is trying to swallow North America, the unstoppable geological disaster, the continent under siege. North America isn't just sinking from rising seas, it's being swallowed from below. What was once thought to be the most stable landmass on Earth is showing signs of collapse at its very roots. Satellite altimeters and tide gauges tell one story, the Gulf Coast settling lower each year as the ocean creeps farther inland. But seismic images now show something deeper, stranger, and far more consequential. The continent's ancient foundation itself is falling into the mantle. This isn't one isolated disaster, but a slow-motion struggle between the Earth's surface and its interior. Beneath New Orleans, Houston, and the coastal plains, the crust bends downward as molten rock and sinking slabs tug from below. The ground we call home is fighting a gravity-driven war invisible to the eye. And what's new isn't the process, is that for the first time, thanks to real-time seismic tomography from the EarthScope project, we can actually watch the continent deform as it happens. The map of North America is still changing, but now we can see the machinery behind the motion. Far inland, something else stirs, a revelation made possible only recently. Seismic instruments from the EarthScope project are capturing strange living shapes inside the continent, dense plumes sinking, molten pockets stirring, and ancient slab fragments cascading toward the mantle. Beneath the quiet fields of the Midwest, the supposed immovable root of North America is thinning, dissolving from within. Scientists call the process Cratonic dripping, and while it sounds delicate, the scale is continental. Vast portions of the planet's deep lithosphere are detaching and falling back into the mantle below. What we once assumed to be the most stable real estate on Earth is, in truth, deforming right now, and for the first time in human history, technology lets us watch it in real time. For most of human history, continents were seen as fixed, eternal platforms. Mountains rose, volcanoes erupted, but the continental core was supposed to be timeless. Now seismic imaging from projects like EarthScope, vast networks of sensors blanketing the United States, has begun to tell another story. Under the Great Plains in the central U.S., tiny but persistent anomalies in seismic waves reveal plumes of dense material sinking thousands of feet below the surface. They move at geological speeds, centimeters per year, but over millions of years they can reshape the planet's skin. What we think of as stable land is in truth only a temporary balance between buoyancy and gravity, between hot rising mantle and cold descending stone. To understand how North America reached this point, we have to rewind 200 million years when the entire landmass was sliding west across a shifting ocean floor. Beneath it, an enormous oceanic plate, the Farallon, was being pulled downward, reshaping the continent above. Most of that plate has been swallowed by the mantle, but its remnants still haunt Earth's interior, twisting mantle currents and altering how the continent floats. Along the surface, its surviving fragments, the Juan de Fuca, Cocos, and Rivera plates, still dive beneath the western margin, fueling volcanoes and quakes from Alaska to Mexico. Others linger deep below as cold, dense fossil slabs stretching hundreds of kilometers across. Their gravitational pull influences mountain building, internal sagging, and even subtle motions as far inland as the Midwest. In a very real sense, the continent still dances to the Farallon's ghost, an ancient plate that continues to guide the rise of the Rockies, the tension in Cascadia, and the slow sinking that marks the Gulf. What lies beneath directs what we see on the surface. That ancient subduction didn't just build mountains, it rewired the continent's underbelly. The Farallon's descent pumped water and volatile elements into the mantle, weakening the once impenetrable root of the North American craton. Over time, that weakening allowed parts of the deep lithosphere to peel away and drip downward, just like wax melting under heat. Computer models now suggest this slow unzipping is still occurring, a geologic leak at the base of the continent. The process is too slow for us to feel, yet fast enough in Earth's timescale to alter coastlines, redirect mantle flow, and change the crust elevation. It's like the continent is sagging into its own shadow. Meanwhile, the surface tells its own side of the story, inch by inch. Every year that the deep Earth drags downward, the ocean presses farther inland. Along the Gulf of Mexico, where the crust was already stretched thin by ancient rifting, the land now sags like a collapsing hinge. By 2050, NOAA projects as much as 10 to 18 inches of additional sea level rise along the Louisiana and Texas coast, twice the national average, enough to submerge entire neighborhoods. Some of that rise is global, caused by melting ice and thermal expansion, but a significant part is local. The crust itself is sinking. It's the same deep mantle war playing out on the surface, climate change from above, tectonic weakening from below. The Gulf Coast isn't just losing ground to the ocean, it's being tugged downward by the continent's own subsiding skeleton. It's a double assault, the visible floodplain version of the same unseen struggle happening miles underfoot. What's unnerving is that these two stories, the deep earth descent and the coastal subsidence, aren't separate. They're chapters in the same conversation between the mantle and the surface. The mantle's convective flow, influenced by the ghost of the Farallon Plate, may very well be tugging the continent downward. Beneath the Mississippi Valley, seismic images show mantle material moving in patterns that match measured land subsidence above it. The sinking land we see from space may be the slow echo of mantle currents far below. So when we say the Earth is trying to swallow North America, it's not a metaphor. The continent stands on a restless foundation of moving rock, one that's been patiently reshaping itself since before the dinosaurs vanished. Geology has no hurry, but it never stops. And somewhere between the Gulf's rising waters and the Midwest's sinking roots, the future outline of the continent is already being drawn. The western threat defining the Cascadia Subduction Zone. If the continental interior is sagging in silence, the continent's western edge is humming with tension. Off the coast of Oregon, Washington, and British Columbia lies a fault so vast and so quiet that for centuries it seemed harmless. No rumbling, no explosions, no quakes worth remembering. People built cities, ports, and glass towers across its span as if it were dead. But it isn't. It's the Cascadia Subduction Zone, a 600-mile stretch where the remnants of the ancient Farallon Plate, now called the Juan de Fuca Plate, slides beneath North America. And it's loaded. The story begins underwater where the seafloor itself bends down into the earth. On one side is the cool, dense oceanic crust of the Juan de Fuca Plate, drifting eastward from the Pacific spreading ridge. On the other is Earth's continental armor, thick, buoyant, and dragging west. When they meet, the oceanic plate dives, scraping under the continent at barely a few centimeters per year. To a human, that speed feels glacial. To geology, it's a conveyor belt, one that constantly generates strain. And in Cascadia, that strain has been locked for more than 3 centuries. For most subduction zones around the world, places like Japan, Chile, or Sumatra, the boundaries speak through tremors. They creak, groan, release. Cascadia doesn't. It has almost no small earthquakes on its interface, meaning the two plates are stuck, fused together by incredible friction. Every millimeter the ocean plate tries to slip carries the equivalent of thousands of nuclear bombs of energy, quietly building elastic tension in the overlying crust. Seismologists describe Cascadia as fully coupled, the most polite possible term for a time bomb. They know what it can do because it has done it before. In the winter of the year 170, without warning, the locked fault ripped free in a single massive rupture. The entire margin from Northern California to Vancouver Island lurched westward by up to 40 meters. The seafloor heaved upward, displacing billions of tons of water. Japan's coast recorded the result as a mysterious midnight tsunami with no local earthquake, a ghost wave that puzzled officials for centuries. Only when geologists in the Pacific Northwest began studying ghost forests, stands of drowned trees killed suddenly by saltwater incursion, did the two events line up. The giant wave in Japan matched perfectly with the death of Cascadia's coastal forests. The date was January 26, 170. The magnitude, about 9. That quake reshaped the entire Pacific coast. Coastal villages were obliterated, river deltas dropped, and lowlands sank permanently below sea level. In Oregon and Washington, peat layers preserved the abrupt switch from forest soil to tidal mud, physical proof that the land itself dropped as the plate boundary released. The next quake hasn't happened yet, but according to the average recurrence intervals measured in offshore sediments, it's due somewhere between now and the next century. To understand why Cascadia is so powerful, you have to imagine the geometry of the collision. The Juan de Fuca Plate isn't just thin crust, it's part of a vast descending sheet extending hundreds of miles inland and down into the mantle. Seismic tomography shows it bending beneath the continent like a wet carpet being shoved under a door. Above it sits a thicker wedge of continental crust that behaves elastically, flexing downward as the oceanic slab pushes beneath it. That flexure creates the coastal mountain ranges and the subtle downward tilt that makes the land seem to bow toward the sea. In slow motion terms, North America's margin is literally being bent backward, storing energy like a drawn bowstring. Farallon subduction laid the groundwork for this centuries ago. When that older plate fragmented, its final pieces became the small modern plates still subducting today, but their force remains immense. The remnants drag cold material deep into the mantle, prompting melting that fuels the Cascade volcanoes, Mount St. Helens, Mount Rainier, Mount Hood, all perched in a line tracing the trench's inland projection. Each mountain is evidence of the same plumbing system, seawater-soaked rocks descending, melting, and sending magma upward through weakened crust. The line of volcanoes is the visible rim of a far deeper engine, and it's that deep engine where things connect back to the rest of North America. Beneath the subduction zone, mantle flows redirected eastward, curling under the continent's interior, where the old Farallon slabs still linger. That circulation doesn't stop at the coast. It influences how the continent flexes thousands of kilometers away. Some geophysicists think the same convection loops feeding Cascadia's underbelly may also be helping the Midwest drip inward, the deep currents tugging at the Craton's base. From top to bottom, it's one continuous conversation, subduction at the edge, dripping and sagging in the heart. But the edge is always where the energy collects first. Right now, the Juan de Fuca plate dives beneath the continent at a rate of about 4 centimeters per year. Satellite GPS stations onshore show the crust being slowly compressed towards east, each point moving a few millimeters annually. The land is literally bending like the antlers of a spring under weight. When inevitably the locked section slips, that bent crust will rebound westward by several meters in seconds. The entire coastline will jolt downward, the offshore ridge will snap upward, and the ocean will rush in. Communities across the Pacific Northwest live directly on top of this loaded fault. Portland, Seattle, Vancouver, they all sit on ground that will be shaken violently when Cascadia releases. Coastal towns like Seaside and Long Beach are within the zone that will drop nearly a meter during the quake, effectively sinking beneath the next high tide. The wave that follows, up to 30 meters high in some models, will reach shore within 15 to 20 minutes. In low-lying parts of Oregon, that's less time than it takes to run from the beach to high ground. What makes this threat unnerving is the silence. Unlike California's San Andreas, which pops frequently with small quakes, Cascadia gives almost no warnings that normal life can feel. Its signals are faint. Tremor waves that pulse deep underground every 14 months, imperceptible to humans, and a slow slip that seismometers detect as subtle ground drift. Researchers compare it to a person's heartbeat during deep sleep, the only sign that something alive waits beneath the calm surface. Modern science has transformed how we see this hidden monster. Ocean-bottom seismometers and pressure sensors now track minute changes in the trench, revealing areas that are creeping and others that are locked solid. Coastal GPS arrays show elastic strain building year by year. Even gravity measurement from satellites detect tiny bulges along the margin where the land is being compressed. Piece by piece, the evidence paints the same picture. Energy is piling up along the full length of Cascadia, and none of it has yet been released. Offshore cores taken from deep ocean basins contain thin layers of sand transported by ancient tsunamis. Counting those layers gives a rough timeline of past megathrust events, 41 in the last 10,000 years. That's roughly 1 every 2 to 5 centuries, though the spacing is irregular. Some pairs came only a century apart, others waited nearly a millennium. The last one, in 170, was right in the middle of that rhythm. Statistically, the next could come tomorrow, or a century from now, and the magnitude is only part of the danger. Cascadia's structure guarantees that when it fails, it won't rupture cleanly. Segments may break one after another, propagating north or south in a cascade of shocks. That's how it gets its name. Each segment's failure sends more stress down the line, like tearing fabric that refuses to stop ripping. Computer models suggest the rupture could last up to 5 minutes, 5 full minutes of the continent vibrating like a tuning fork while the coast collapses. For indigenous communities of the Pacific Northwest, this cycle was never a mystery. Oral histories from coastal nations describe a night when the ground shook, the sea withdrew, and then a wall of water came. Villages vanished. Generations retold the story as both memory and warning. Western geology only caught up centuries later when they realized. These stories held precise physical detail. The simultaneous shaking and flooding, the sudden silence, the wave that traveled beyond sight. Modern science simply provided the timestamps. Today, major cities on the fault line live with one foot in denial and the other in preparation. Engineering codes in Seattle and Portland have been rewritten, but retrofitting old buildings lags decades behind. Critical lifelines, highways, fuel terminals, ports still sit atop soft river sediments that will liquefy during strong shaking. Bridges are designed for magnitude 7 stress, not 9. Even the power grid connects through substations built before Cascadia was fully recognized. Emergency planners estimate coastal evacuation windows in minutes, not hours, and training drills are sporadic. For many, the last disaster seems too far in the past to feel real. Yet the land keeps reminding anyone who looks closely that it's still moving. Along the Oregon coast, tide gauges show the land sinking by millimeters each year, the exact reverse of uplifts seen in the Olympic Mountains farther north, proof of the slow flexing that precedes rupture. Offshore sonar has mapped huge pressure ridges growing at the accretionary wedge, where mud and sand are scraped from the descending plate and piled like a rising scar. These are the quiet signs of strain reaching its limit. There's also the volcanic signal. Deep beneath the Cascades, magma chambers are inflating slightly faster, measured in parts of Mount Hood and South Sister by satellite interferometry. While not a direct predictor, that inflation hints at stress redistribution within the whole arc system. The subducting plate dehydrates as it slides, releasing water that lowers the melting point of mantle rocks. That process pulses with each subduction rhythm. So even though the next big quake will begin offshore, its repercussions stretch inland through the volcanic chain, possibly triggering eruptions months or years afterward. The interconnection becomes haunting when you imagine the continental scale. The same Farallon Plate that once plunged under California 50 million years ago is still sinking today beneath the continent's core. As it drags cold slabs into the mantle, warms and breaks apart, it distorts flow patterns that affect everything from Yellowstone's Hotspot to the slow dripping beneath the Midwest. Cascadia is simply the still active frontier of that ongoing descent. Every megathrust quake there sends new shockwaves of adjustment through the underlying mantle, subtly altering convection far from the coast. The tremor of 170 likely rippled deep beneath the continent, a whisper that may still echo in today's mantle imaging as disturbed flow patterns. What all this means, in slow but certain terms, is that subduction doesn't end where the ocean disappears. The plate keeps diving, and its influence follows deep under North America, pulling on the continental route and changing how the crust floats within the planet's vast circulating interior. The visible earthquake is just a punctuation mark. The sentence continues in molten rock miles below. Cascadia, therefore, isn't just a regional hazard. It's a mirror of the continent's deepest mechanics. It shows how the western edge, constantly consuming oceanic crust, helps drive the entire system of uplift, subsidence, and internal dripping that defines the continent under siege. The next great rupture will be a surface-level reminder of a much older conversation between subducting slab and rising plume, between gravity's pull and mantle buoyancy. For now, we sit in the pause between sentences. The instruments keep ticking, the land keeps folding, and somewhere offshore, the ocean floor continues to creep downward, grain by grain, into a future quake that will one day speak for centuries of silence. The sleeping giant, the mechanics of the megathrust earthquake. When geologists talk about a megathrust, they don't mean hyperbole. They mean a fault so large that the entire edge of a continent can move at once. That's what waits offshore the Pacific Northwest, a sleeping giant of compression that has been winding tension since before the United States existed. The Cascadia Subduction Zone isn't just a line on a seafloor map. It's the seam of two planetary machines grinding together in silence, storing energy the way a glacier stores gravitational fall. Every millimeter of motion adds to the future violence. Deep underwater, the boundary looks nothing like the tidy crack we imagine. Instead, it's a landscape of folds and ridges, soft sediments squashed into sheets. As the Juan de Fuca plate dives, it drags these layers down until they buckle and shear. Each inch of descent tightens friction against the continental plate that rides above. Eventually, the contact locks. For decades, sometimes centuries, the plate continues its slow dive, but the upper plate refuses to budge. It bends instead, deforming elastically inch by inch until one day it snaps. In that instant, centuries of compression become seconds of acceleration. The seafloor vaults upward. The continental shelf jolts westward. Miles of coastline drop as the overriding plate rebounds. The movement, an average of several meters, takes only a few minutes, but is enough to shift the position of entire cities relative to the ocean. The earthquake we experienced, the shaking, the sound of buildings slamming, the power lines whipping, is just the crust audible protest. The true action happens far below, in the subtle rearranging of rock masses the size of countries. Scientists now believe that the 170 Cascadia quake ruptured nearly the entire subduction interface from Northern California to Vancouver Island in one go. The first tremor likely started offshore present-day Oregon, where the locking was strongest. As that patch failed, it transferred stress north and south like tearing paper. Within minutes, the rupture had raced more than 600 miles, releasing energy equivalent to several thousand nuclear bombs. Seismic models suggest vertical displacements of up to 30 feet along parts of the trench, a catastrophic reshaping of the seabed that gave rise to its trans-Pacific tsunami. The mechanics of such an event start long before the crack. Everything begins with subduction geometry. Cascadia's shallow dip, barely 15 degrees beneath the continent, means that the plates overlap across an enormous contact area, perhaps 100,000 square miles. The friction across that surface is immense. That's why when it fails, it does so as a megathrust, not a mere quake. In technical language, slip on the interface propagates as dynamic rupture, driven by rapid reduction of frictional strength. But in human terms, the land simply lurches sideways and gravity does the rest. During the first 10 seconds, stress concentrates at the lock disparities, jagged points where the two plates cling stubbornly together. When those break, they release shock fronts that accelerate rupture speed to nearly 2 miles per second. Seismic waves of different types, compressional P waves, slower shear S waves, and complex surface waves, radiate outward. P waves hit first, subtle pre-tremors that might rattle hanging lamps. Then come the S waves, snapping infrastructure, twisting buildings. Finally, surface waves roll through, undulating like an invisible tide through valleys and mountain ranges. Structural engineers often describe these as the killer waves because their long periods resonate with tall buildings, bridges, and port cranes. Seismometers record another faint signal that accompanies megathrust, a deep, infrasonic hum known as the seismic rumble. In Cascadia simulations, it lasts several minutes as energy reverberates between crust and mantle. Coastal areas will experience ground shaking for at least 4 to 5 minutes, an eternity when roads, bridges, and pipelines are tearing apart. After the shaking subsides, what follows is worse, the sea's response. Tsunamis begin not as towering walls visible from afar, but as subtle shifts in the water column miles above the rupture. When the seafloor suddenly lifts and drops, it displaces a mass of water equal to billions of tons. That disturbance propagates outward at jet airplane speeds, around 500 miles per hour in deep ocean. For a while, the surface barely ripples. The wave's energy is hidden below. As it approaches the shallower shelf, that energy is compressed upward, forcing the wave to rise dramatically. Within 20 minutes, the Pacific Northwest coastline would face a series of surges that may exceed 30 meters in extreme locations. Modern tsunami models include complexities that early researchers could only guess at: submarine landslides, trench splay faults, and sediment collapse zones that further amplify the water displacement. In recent years, detailed bathymetric mapping of the accretionary wedge has revealed steep scarps and gas-rich sediments capable of collapsing during the quake. Those secondary slides could double local wave heights in certain estuaries and bays, a deadly multiplier for coastal communities like Newport or Crescent City. An overlooked part of megathrust mechanics lies in what the land does after the shaking. The abrupt subsidence of coastal terrain by 1 to 2 meters means that tide lines permanently shift. Research into the 170 event shows drowned marshes stretching for miles inland, their tree trunks still preserved in clay. The process is geometric. When the locked subduction zone gives way, the entire forearc, the region between the trench and the volcanic arc, flexes downward. The hinge line runs roughly beneath the coast range. East of it, the crust rises. West of it, the crust sinks. That is why one region may uplift dramatically while another vanishes beneath the tide. At broader scale, the megathrust ripple reaches far into the continent. GPS simulations show that as the outer margin rebounds westward, the interior briefly oscillates, redistributing stress hundreds of kilometers inland. This reverberation can trigger secondary faults in Oregon's Basin and Range Province, or even modulate activity along the San Andreas farther south. The Earth behaves elastically, and large displacements in one place send elastic waves that alter pressure elsewhere. North American plate, though solid by human standards, moves like a slow jelly under such massive forces. Beneath the crust, mantle processes also react. When the Juan de Fuca slab suddenly slips, it doesn't merely slide, it jerks deeper, enhancing subduction velocity for a time. That acceleration perturbs the mantle wedge above it, allowing older magma to rise or depressurize rapidly. In volcanic systems like Mount St. Helens or Hood, that decompression can resuscitate dormant chambers. Seismic gas signatures recorded at volcanoes after major earthquakes in Japan and Chile show increased emission rates linked directly to similar megathrust rearrangements. For Cascadia, that means the quake will be followed by years, possibly decades, of magmatic adjustment. From a geodynamic standpoint, the sleeping giant is part of Earth's self-balancing act. Subduction zones recycle oceanic crust back into the mantle, but each cycle's release, each megathrust, is the price of that recycling. On timescales spanning millions of years, these events maintain planetary equilibrium. Old lithosphere sinks, continents drift, heat escapes. Its violence serving a cooling planet. Yet on human timescales, it's catastrophe. Understanding those dynamics has become urgent science. In the last 2 decades, instruments along Cascadia's offshore slope have detected slow slip events, pulses of motion that occur roughly every 14 months. These slow earthquakes relieve tiny amounts of stress, moving the plate boundary by a few centimeters over weeks. But they also indicate how close certain patches are to failure. Each episode is like the faint click of a wind-up spring nearing its limit. The Cascadia Initiative, a collaboration of U.S. and Canadian agencies, now maps these zones with a dense grid of ocean-bottom seismometers. Their data suggests the fault is segmented, with some regions accumulating strain faster than others. The central portion offshore of Oregon appears most locked, a prime candidate for nucleation of the next rupture. Despite the detail of modern imaging, predicting exactly when the event will occur remains impossible. The megathrust operates in geological time, ignorant of calendars, yet we understand its pacing better than ever. Stratigraphic evidence from coastal lakes and offshore cores reveals that large Cascadia earthquakes cluster in sequences. Sometimes decades of smaller quakes precede a major one, like foreshocks gathering courage. In others, a sudden giant ends centuries of calm. The system behaves more like a living organism than a machine, periodically releasing built-up energy to survive its own existence. If all of this sounds abstract, consider the tangible arithmetic of stress. The Juan de Fuca plate converges toward North America at about 4 centimeters per year. If the contact zone last ruptured 323 years ago, that's about 13 meters of plate convergence that has gone unrelieved. Typical slip during a megathrust is 15 to 20 meters. In theory, we are already within the margin of over-accumulated strain. In practice, that means the next rupture will need no invitation. It's already overdue by Earth's internal standards. What happens after the quake may be as consequential as the quake itself. The elastic rebound will throw much of the region into long-term vertical motion, some areas uplifting for centuries, others sinking as sediments compact.
River mouths will migrate, deltas will vanish,
and entire ecosystems will reset. New wetlands will replace forests, salt intrusion will reach far upstream. For human systems, ports, pipelines, roads, the real destruction will come not only from the initial shock, but from how the land continues to rearrange for years afterward. Geophysicists also note that megathrusts set off subtle oscillations in Earth's rotation. When massive plates shift, they redistribute planetary mass. The 2011 Tohoku quake in Japan shortened Earth's day by 1.8 microseconds and moved its axis by several centimeters. Cascadia, though smaller, could produce measurable effects of its own, possibly altering local gravity fields. Such tiny metrics remind us that our continents are not fixed coordinates, but mobile structures behaving under laws of fluid dynamics and moment of inertia, physics on a planetary stage. In some sense, the sleeping giant is misnamed. It isn't asleep, it's constantly turning in its rest. The seafloor heaves imperceptibly, gases seep from splay faults, and plankton bloom on nutrient-rich upwellings fed by minor tremors. Even the silence is a kind of motion, too slow for our bodies to detect. The megathrust merely represents the moments when that motion accelerates to human scales, when the geological clock briefly ticks audibly. For communities in the Pacific Northwest, that ticking has become the rhythm of preparation. Every new school built along the coast now has vertical evacuation routes etched into its blueprint. Siren tests ring on the first Wednesday of each month. Some towns have practiced tsunami walks where residents follow map lines to higher ground within 15 minutes, yet elsewhere complacency persists. Hundreds of thousands still live within known inundation zones. Dozens of hospitals, fuel depots, and data centers lie on ground predicted to liquefy. It's a modern paradox, civilization expanding over the very fault that will someday reset it. On a planetary scale, these megathrusts are reminders of how thin continental security truly is. The Farallon plates that began sliding beneath the continent 165 million years ago initiated a chain of cause and effect that has never stopped. The fragments still sinking today define not only the mountains and volcanoes we see, but the hazard that waits beneath them. Cascadia's next rupture will be felt across the continent in ways both physical and psychological. For the minutes of its shaking, the illusion of permanence will dissolve. And yet, in geological cycles, such events are creative as well as destructive. The uplifted ridges that rise after a megathrust form new coastlines. Drowned valleys become estuaries teeming with life. The forces that flatten cities also sculpt landscapes. North America owes much of its shape to precisely these kinds of convulsions repeated countless times through deep history. The continent is forged in disaster, stabilized in recovery, only to be tested again. So when we call Cascadia the sleeping giant, we're really describing Earth's breathing. Long, slow inhalations of release. Somewhere offshore, that breath is still drawing in. The plates pressed together by another fraction of an inch. The crust flexes a little more and silence deepens. Someday, maybe tomorrow, maybe centuries from now, exhalation will come. And when it does, the entire edge of a continent will move. The eastern anomaly, why the new Madrid zone, is still a disaster waiting. Every part of North America has its own rhythm of movement. Slow sinking in the Gulf, steady compression along the Pacific, subtle stretching near the Rockies. But deep in the country's center, far from any plate boundary, there's a fault system that refuses to stay quiet. It sits beneath the Mississippi River Valley, surrounded by soft farmland and calm skyline. There are no volcanoes, no visible mountain scars, and yet 200 years ago it nearly tore the continent in half. In the winter of 1811, the region around the small frontier town of New Madrid, Missouri, began to shake. At first, it was mild, an unfamiliar shiver that rattled dishes and sent birds into the sky. But by December 16th, the shaking turned violent. Trees snapped like twigs, the ground cracked open, and the Mississippi itself seemed to lose its direction. Eyewitnesses described waves rolling across the soil, an entire forest sinking below swampy water. The quake was strong enough to ring church bells in Boston, 1,000 miles away. And that was just the beginning. The first shock, estimated near magnitude 7.5, was followed by two more of equal or greater strength, one in late January, another in early February 1812. By then, aftershocks were constant, numbering in the thousands. The town of New Madrid was destroyed. Across an area larger than Pennsylvania, the landscape permanently changed. New lakes formed, river channels shifted, and sections of land rose or fell by several meters. Many thought the world was ending, but the truth was older and stranger. The new Madrid seismic zone sits astride an ancient wound in the continent's crust, a line left behind by a failed attempt at continental breakup more than 500 million years ago. Back in the Proterozoic era, the heart of North America tried to tear itself apart. Magma pushed upward in what geologists now call the Reelfoot Rift, a massive crack running northeast-southwest beneath what is today Missouri, Arkansas, Tennessee, and Kentucky. The rift never made it to the ocean. The tearing stopped midway, but the scar remained, buried under layers of younger sediment. To the casual observer, the Midwest seems like the opposite of a tectonic frontier. But at depth, the crust beneath the Mississippi embayment is riddled with ancient faults, frozen fractures that occasionally wake when the deeper mantle stirs. The same mantle circulation that drags at the base of the North American Cratonic, thinning it under the Midwest, exerts gentle tension on this old rift. When stress builds, those prehistoric cracks can reactivate, producing earthquakes in places where nobody expects them. Seismic imaging from modern arrays shows that the crust under New Madrid is thinner and more fractured than previously believed. At about 15 to 20 miles deep, the boundary between crust and mantle, known as the mohole, is warped downward into a gentle bowl. That warp helps concentrate stress from above. Think of it as a weak hinge and a heavy door. The weight of the continent presses unevenly, and every so often the hinge slips. The 1811 to 1812 sequence wasn't the first time the hinge gave way. Geological evidence, the kind written in sand blows, liquefaction layers, and deformed river terraces, shows at least 4 similar events in the last 2,000 years. Carbon dating of those deposits puts major ruptures around the years 900, 145, and 1811. The intervals aren't regular, but they're close enough to suggest a repeating cycle of strain accumulation roughly every 500 years. To scientists, that means one thing: it will happen again. The debate isn't whether the fault is dead, but when awake. GPS networks in the central U.S. record minute ground motions, fractions of a millimeter per year, that some researchers attribute to post-seismic relaxation, the crust still settling from the last great quakes. Others argue it's ongoing strain buildup from mantle flow pushing sullied north-south under the region. In both interpretations, the forces are active. The question is how fast they're loading the next failure. For the millions who live above this buried fault system, from Memphis to St. Louis, the quiet has bred complacency. Earthquake drills are rare, and few buildings east of the Rockies are designed to handle sustained shaking. Yet computer simulations show that another new Madrid-scale event could devastate the lower Mississippi Basin far beyond what early America experienced. The geology of the region amplifies motion. Thick alluvial sediments vibrate like gelatin, trapping and lengthening seismic waves. When the ground shakes there, it tends to keep shaking. Federal emergency planners have modeled worst-case scenarios for decades. One assessment by the U.S. Geological Survey projected that a repeat of the 1812 sequence could cause more than $300 billion in damage, collapse 15 major bridges, and leave parts of Arkansas and Tennessee without power for weeks. Unlike western quakes confined to narrow fault zones, the soft sedimentary basin of the Midwest would transmit energy laterally for hundreds of miles. Cities like Indianapolis, Chicago, and even Atlanta could feel swaying tall buildings. But the story of New Madrid isn't just about risk, it's about what it reveals underneath the continent. Seismic tomography, the same technique that exposed Cratonic dripping under the Midwest, has found low-velocity zones directly beneath the New Madrid area. These zones suggest pockets of warmer, partially molten mantle rising from below 300 kilometers deep. Intriguingly, the pattern aligns with the edge of the sinking Farallon fragments imaged farther west. Where the old slab's influence tapers off, upwellings from the mantle seem to rise, tugging subtly on the crust above. It's another clue that what moves in Cascadia eventually echoes beneath the heartland. Some geologists propose that the Reelfoot Rift acts as a stress concentrator in this system, a place where even small mantle adjustments translate into surface quakes. When the Farallon residue drags the mantle down to the west, the flow compensates by circulating upward to the east, pushing gently against the craton's underside. Over centuries, those invisible adjustments retension the old rift. It's a deep earth tug-of-war whose surface expression is periodic catastrophe. In recent years, networks like EarthScope and Carry have recorded thousands of close-to micro-earthquakes in the New Madrid zone. Most are too small to feel, magnitudes 1 to 2, flickering like static on a seismograph. But their distribution sketches a 3-dimensional picture of the fault system, a set of N-echelon segments slanting northeast, each dipping toward the southeast. They connect like a chain of dominoes. If one goes, stress transfers to the next. Historical records suggest that's exactly what happened during the 1811 to 1812 sequence. 3 main shocks in 3 different segments, cascading through the rift system over 2 months. The human impact would be far larger today. In 1812, the region was sparsely populated and most structures were wooden. Now millions live above the same faults, surrounded by pipelines, chemical plants, and interstate arteries. Modern infrastructure adds a layer of vulnerability never before tested in the central U.S. The Mississippi itself, confined by levees and dams, might react unpredictably to sudden uplift or subsidence. Numerical models show potential for avulsions where the river abruptly jumps to a new channel, a possibility that could cripple barge transport and flood farmlands for decades. Even modest tremors remind locals that the fault persists. In 2002, a magnitude 5.1 quake near Sparta, North Carolina, outside the core zone but within the larger eastern stress field, rattled homes as far as Washington, D.C. That event underscored how interconnected old continental faults can be. Pressure released in one region redistributes across hundreds of kilometers through the rigid but elastic North American plate. The continent flexes a single piece. Beneath all of this lies a broader geodynamic context. The same mantle convection that feeds Cascadia Subduction Zone continues east under the continent, where detached remnants of the Farallon slabs still sink. As those slabs descend, they drag cooler, denser rock downward, forcing surrounding mantle to flow in compensating patterns. The return flow curls upward beneath the central U.S., generating subtle uplift and horizontal stress at the base of the crust. Over thousands of years, that stress accumulates along pre-existing weaknesses like the Real Foot Rift. Every few centuries, the system relieves itself through a cluster of earthquakes, then starts reloading again. This continuous cycle suggests that the Midwest isn't as seismically passive as textbooks once taught. It's a dynamic zone responding to deep, ongoing mantle circulation. The Eastern Anomaly, as some researchers call it, represents one of Earth's reminders that tectonic boundaries aren't the only places capable of destruction. The continent's interior, though seemingly inert, records the delayed reactions of its buried engine. If you stand today near Reelfoot Lake, one of the youngest natural lakes in the United States, the surface looks tranquil. Water lilies scattered over still water, herons crossing in silence. But the lake itself is a direct scar from the night the Earth fell downward. It occupies a sagging block created when the land dropped several meters during the 1811 quake. What appears as serenity is in fact frozen violence. Scientists drilling beneath that lake find layers of deformed sediment, marking each great quake like tree rings of disaster. The pattern stops at about 5,000 years ago, after which earlier layers vanished in the ancient river channels. That suggests the cycle has persisted for millennia, long before written memory. Each generation of earthquakes reshapes the landscape, the river, and perhaps even the psychology of the land, then sleeps. When the next one comes, it won't announce itself months ahead. The first P waves will cross the city limits of Memphis in seconds. Power lines will snap, soil will liquefy in the neighborhoods built on old floodplain sand, and levees along the Mississippi will strain against reverse flow. Bridges designed for vertical load will twist sideways, their decks tilting into the river. 20 minutes later, aftershocks will begin, each one a grim echo of the last. All of this, from deep mantle current to collapsing bridge, is part of the same conversation that began with the Farallon Plate. The west still sinks, the center flexes, and the east waits for release. In between, the entire plate breathes, compressing at its edges, exhaling through ancient cracks far from any ocean. That's why the new Madrid zone still matters. It's the hinge that reminds North America it's alive. The silence is temporary, the stillness deceptive. Someday, perhaps soon or centuries from now, the buried scars of an ancient failed ocean will twitch again, and the heart of the continent will shake. The river will waver, the bells will ring, and the earth will whisper the same message it's spoken for 500 million years, that stability is only a pause between movements. Tearing apart the Rio Grande rift and the basin and range extension, the earth tears itself open differently in the western interior. Here, instead of colliding plates like Cascadia, the continent stretches. You can trace the wound across a vast swath of terrain from central Colorado down through Mexico, across Arizona and Nevada, all the way to the deserts of California and northern Mexico. On maps, it appears as a mosaic of long valleys and towering ridges, the Basin and Range province. Each basin is a sunken block of crust. Each range is a block lifted beside it. Together they form an immense corrugated plain, the geological equivalent of stress marks on a bending beam. This is the surface expression of the Rio Grande Rift and its sprawling network of related faults, a testament to how the continent pulls itself apart from within. To the naked eye, it feels stable. Interstate 10 cuts through endless desert flats, distant peaks shimmer in heat. Yet beneath this quiet landscape, the continent is literally thinning. The crust here is stretched by nearly 100% over the last 20 million years, meaning what was once 100 miles across is now almost 200. That stretching doesn't happen because of local faulting alone. It's driven by motion in the deep mantle, the ongoing rearrangement caused by the sinking of the Farallon Plate and the rising of hotter rock from below. The Farallon's descent left behind slab-shaped voids that act like suction zones, pulling the overlying continent toward them and allowing hotter, lighter mantle to rise and return. The Rio Grande Rift marks one of the weakest scenes where that upward pressure succeeded in splitting the crust. The rift itself runs roughly north-south, a 200-kilometer scar beginning near Leadville, Colorado, and ending near El Paso. Along it lie a chain of basins: San Luis, Espanola, Albuquerque, Socorro. Each one a down-drop block flanked by normal faults that tilt outward like jaws opening. Between these basins rise gentle ranges: the Sangre de Cristo, the Manzanita, the Organ Mountains. Every ridge a slice of crust pushed up as its neighbor sank. Satellite geodesy shows that extension continues even today at 1 to 2 millimeters per year, the slow-motion birth of a micro-ocean that never quite forms. To understand how such tearing began, we have to step farther back. As the Farallon Plate slid under North America, it didn't dive steeply. During the Laramide orogeny roughly 70 million years ago, it flattened, traveling hundreds of miles inland before finally descending into the mantle. That shallow subduction compressed the western interior, creating the Rockies. When the slab finally detached and fell away in the early Cenozoic, the pressure it had exerted vanished almost overnight in geological terms. The crust, suddenly free from compression, rebounded outward and upward, but momentum carried it too far. Like a released spring, it began to stretch. The thickened crust thinned, cracked, and blocks began to drop between faults. What we now call the basin and range is essentially the continent's slow recoil from an era of compression. The Rio Grande rift formed along its eastern margin where the thinning crust localized into a narrow zone. Heat flow here is unusually high. Geothermal gradients exceed 40 degrees Celsius per kilometer in places, twice the global average. That excess heat originates partly from mantle upwelling and partly from the thinning of the lithosphere itself, which allows magma to intrude closer to the surface. The Socorro magma body, a partially molten lens about 12 miles deep and 50 miles wide beneath central New Mexico, attests to that ongoing process. It's believed to be the largest active magma reservoir in the continental United States outside Yellowstone. Seismic surveys show periodic uplift above it, sub-centimeter per year pulses indicating the magma chamber inflates and deflates as gases accumulate and escape. To locals, these changes are invisible. To geophysicists, they're the heartbeat of an active continental rift. The Basin and Range province west of the rift exaggerates the same concept on a continental scale, a region of pure extension nearly as big as the lower 48 states. Its valleys, Death Valley, Owens Valley, Snake Valley, are all tilted blocks sliding away from one another on normal faults that dip beneath towering mountain fronts. Between Nevada and Utah alone, there are more than 200 separate ranges, each a product of this rhythmic faulting. Satellite imagery at the surface reveals long, parallel scarps etched like wrinkles, proof of countless earthquakes over millions of years. While most quakes now are moderate, magnitude 6 events still strike occasionally, like the 1954 Fairview Peak sequence that split Nevada's surface for 30 miles, displacing it by 10 feet. What powers this stretching isn't just gravity, but the churning beneath. Seismic tomography and Mantle's Xenolith studies show that beneath the basin and range lies a region of unusually low seismic velocity, evidence of hot, partially molten mantle rising. The detachment of Farallon slabs created space that the mantle quickly filled with buoyant asthenosphere. That in turn weakened the overlying lithosphere, making it easier for faults to slip and the crust to spread. Geodynamically, it's an interplay of uplift from heat and collapse from gravity. As the crust warms, it becomes less dense and tries to rise, but as it rises, it stretches and fractures under its own weight. The cycle feeds itself. In some ways, this slow tearing mirrors what may have happened under Africa's Great Rift Valley today, a continent beginning to divide. The difference is that North America's attempt stabilized before reaching the ocean stage. The extension here has persisted for about 25 million years without producing true seafloor spreading, meaning the crust remains continental though thin to less than 30 kilometers in places. Deep drill cores through Nevada reveal metamorphic core complexes, domes of once deep rock now exposed at the surface. These domes form when extension peels the crust like layers of an onion, exposing rocks that used to lie 15 miles below. Standing atop one, a geologist can literally touch what was once the mid-crust. The picture grows stranger where the Rio Grande Rift intersects other tectonic systems. Near its northern end in Colorado, it blends into the Arkansas Valley Fault Zone, a transfer path tying the rift to uplift in the Rockies. Southward, it merges with faults of the Chihuahua Trough in Mexico, suggesting extension propagates beyond U.S. borders. The pattern of earthquakes confirms it. Swarms in West Texas and northern Chihuahua align perfectly with the projected rift axis. Even the geothermal distribution follows suit. Clusters of hot springs and volcanic centers punctuate its length, from the San Luis Valley's volcanic fields to the Valles Caldera near Los Alamos, one of the youngest supervolcano remnants in North America. The Valles Caldera itself is a reminder of how rifting and volcanism intertwine. Around 1.25 million years ago, an enormous eruption emptied a magma chamber 20 miles wide, collapsing the surface into a circular depression. Ash from that blast blanketed parts of Kansas. The caldera's presence along the rip indicates that as the crust stretched, magma found its easiest exit along the faults. Today, hydrothermal systems still percolate inside, heating groundwater that surfaces as steaming vents. The volcano sleeps, but geodesy shows the caldera floor subtly rising, perhaps recharging. Modern instruments capture how alive this system remains. Continuous GPS stations across New Mexico and Arizona register outward motion, points on either side of the rip drifting apart by about 2 millimeters annually. Inseer satellite radar deflects subtle vertical changes within certain basins, indicating ongoing fault creep. Micro-seismic arrays detect thousands of tiny tremors each year near Socorro, signals often linked to fluid movement rather than brittle failure. Taken together, these data paint a continent that hasn't finished adjusting. The stretching that began tens of millions of years ago continues, flexing the land as mantle convection shifts beneath. The basin and range's current tectonics also influence hazards we rarely associate with the interior: earthquakes, volcanic eruptions, even changes in groundwater systems. In Nevada's Walker Lane, a broad zone running parallel to the Sierra Nevada strain transfer from the southern San Andreas Fault may eventually redirect Pacific North America plate motion inland. If that happens, parts of the basin and range could evolve into a new plate boundary millions of years from now, replacing the San Andreas as the main line of motion. In a sense, the continent could split once more, the Pacific carving northward through these deserts toward the Rockies. From a human perspective, the region's slow motion feels irrelevant. Towns rise and vanish before the ground moves a few feet. Yet the subtotal of that creeping deformation is profound. Many basins now lie thousands of feet lower than when they began forming. Crustal thinning has altered hydrology. Tilting affects river drainage, while fault scarps act as aquifer barriers. Las Vegas owes its groundwater basins to these ancient structures. So does much of the Southwest geothermal potential. Power plants in Nevada tap superheated fluids circulating along fault zones that owe their existence to this long-term pulling apart. From orbit, astronauts describe the American Southwest as a quilt of color and texture, linear valleys shadowed by ridges. Each line is a fracture in the continental canvas. But to geologists, those lines trace an ongoing experiment in plate dynamics. What happens when a plate that was once compressed begins to relax while its underside continues to sink? The Farallon legacy, still diving into the mantle, tugs at the western half of the continent while gravity and heat stretch the surface above. The Rio Grande Rift and Basin and Range are simply the visible seams in that tug-of-war. Curiously, their subsiding basins echo what happens along the Gulf Coast, though driven by opposite mechanisms. There, the surface sinks as sediments compact and the lithosphere buckles downward underweight. Here, it sinks because the crust is thinning and sliding apart. Yet the result: increased vulnerability to flooding, shifts in water tables, and change in topography is not so different. Both edges of the continent respond to the same deep command: adjust to new balance as the interior drifts. When you drive from the jagged ridges of Nevada into the Rift Valley around Albuquerque, you're crossing an active scar of geological reequilibration. Beneath the tires, faults are still creeping, breath slow, adjusting to mantle currents that no human senses. The torn landscape tells the same story everywhere. Mountains lifted in one era, valleys born in another, all pieces of a continent learning how to settle after centuries of compression. In time, millions of years hence, this region could either stabilize like the ancient Cretan to its east, or continue splitting toward a new oceanic boundary. For now, it remains mid-sentence, a landscape caught between forces that never quit pushing and those that never quit pulling. Across Western America, from California's eastern escarpments to the Rockies' foothills, the silent expansion continues. Roads buckle, rivers shift course by inches a century. Volcanoes breathe through geothermal vents, and the mantle circulates below like thick wind. The same processes that built mountains are now in reverse. peeling them open, lowering the land bit by bit. The continent, it seems, is testing its own strength. The Rio Grande Rift and the Basin and range stand as reminders that even in the heart of apparent emptiness, the planet is alive, rehearsing the next chapter of its slow disassembly. The heat below, connecting tectonics to the Yellowstone supervolcano. In the northwest corner of Wyoming lies a landscape that tells a double story, one of extraordinary creation and catastrophic potential. Yellowstone National Park, home to erupting geysers and boiling springs, sits atop one of Earth's most active mantle hotspots. Beneath the serene forest and shimmering lakes, the crust swells over a reservoir of molten rock large enough to refashion continents. But Yellowstone isn't simply a local curiosity. It's the visible mark of a process that ties directly to the same tectonic forces tearing at the edges of North America. The energies that feed the Cascadia Subduction Zone and the dripping crag beneath the Midwest also converge here. The difference is that Yellowstone's expression is upward instead of downward, a plume, not a sink. Beneath the park, seismic tomography reveals a column of hot mantle rock rising from nearly 900 kilometers deep, one of the clearest examples of a modern mantle plume on the planet. The plume's path isn't a straight vertical cylinder, but a leaning conduit, deflected to the northeast by the same sinking Farallon remnants that drag mantle westward under North America. As that plume rises, it melts parts of the overlying lithosphere, creating gigantic magma reservoirs stacked within the crust. The upper chamber, roughly 50 kilometers wide, sits only a few miles beneath the surface. Together, these bodies feed the region's hydrothermal features, Old Faithful, the Grand Prismatic Spring, thousands of fumaroles and sulfur vents. What tourists see as an alien landscape of steam and color is, in truth, a pressure valve for one of Earth's largest volcanic systems. To grasp why it formed where it did, think of North America as a raft drifting west across a convecting mantle sea. 65 million years ago, that drift carried the continent over the Farallon Subduction Complex. When remnants of the Farallon eventually detached and sank, they created gaps in the mantle flow. Into those gaps, buoyant, hot rock rose, the same circulation that powers hotspots worldwide. As the continent continued its westward motion, this fixed upwelling point scorched a moving trail across the interior. The chain of volcanic scars that stretches from the Oregon-Nevada border to Yellowstone marks that path like footprints frozen in lava. The Snake River Plain, each volcanic center younger toward the northeast, each one recording the continent's slow passage over the hotspot. The last three major caldera-forming eruptions at Yellowstone occurred roughly 2.1 million, 1.3 million, and 640,000 years ago. Each erupted more than 1,000 cubic kilometers of material, hundreds of times greater than Mount St. Helens in 198. The 640,000-year event excavated the current caldera, a crater 40 miles across whose rim now hosts mountains, lakes, and herds of bison, grazing obliviously above frozen explosion scars. Ash from that eruption blanketed much of North America, forming layers still visible in road cuts across the plains and sediments as far east as Louisiana. The scale defies simple imagination. Imagery of darkness at noon, skies raining glass, and landscapes buried under meters of ash. Yet in geological terms, these were routine acts of mantle readjustment. Today, the system beneath Yellowstone hasn't gone quiet, it's only breathing in longer intervals. Continuous GPS records show that the caldera floor rises and falls by centimeters each year, slow pulses of inflation and deflation reflecting magma and gas migration within the chambers below. Earthquakes tremble through the crust daily, most too small to feel, but collectively mapping the movement of fluids and rocks. In 1959, a magnitude 7.3 quake near Hebgen Lake on the park's western edge revealed the region's capacity for major tectonic motion. Its landslides buried campers and rerouted rivers, a terrestrial echo of the forces rearranging the crust from beneath. What makes Yellowstone uniquely dangerous isn't its frequency, but its connection to the entire plate structure beneath North America. The mantle plume's upward surge coincides spatially with a transition zone in the subducted Farallon slab. Seismic imaging suggests that parts of the old plate lie stagnant beneath the continent, forming a barrier that redirects rising heat sideways. Where that heat encounters thinner lithosphere, especially the stretch left weakened by ancient Farallon subduction, the plume intensifies partial melting. In that sense, Yellowstone owes its vigor not solely to deep mantle convection, but also to the ghost of a sinking plate below. The continent's underbelly operates as both funnel and amplifier. When molten rock accumulates in large volumes, pressure rises until fractures in the crust provide release. Most of the time, that release comes as hydrothermal eruptions or minor lava flows. Occasionally, however, the roof of the magma system fails. During the Great Caldera event, that collapse produced an instantaneous void into which the surface fell, forming a depression dozens of kilometers wide. The eruption cloud rocketed upward into the stratosphere, distributing ash globally, while pyroclastic flows raced outward at highway speeds. Afterward, the emptied chamber slowly refilled, beginning the cycle again, a planetary breathing on the timescale of 500,000 years. Geochemists studying gases escaping from Yellowstone's vents have traced isotopic ratios consistent with primitive mantle sources, meaning the plume taps material far deeper than typical crustal melts. That chemistry ties the system directly to Earth's interior, linking it with the same upwelling currents that influence opposite sides of the continent. While the Farallon remnants sink and drag downward forces under the Gulf and Midwest, Yellowstone represents the compensating upward stream, keeping the planet in thermal balance. The sinking lithosphere and the rising plume are two halves of one convective cell, their interaction driving the long-term warping we witness at the surface. Satellite gravity data show that the crust around Yellowstone is slightly elevated, a vast dome trailing several hundred kilometers beyond the park boundaries. That uplift isn't a static bulge. It migrates gradually eastward along the path of Mantle flow. Some geophysicists interpret it as a thermal bow wave moving ahead of the plume's ascent. In simpler terms, the heat source traveling below the continent subtly lifts and weakens the overlying crust long before an eruption, laying groundwork for future deformation across the region. Part of why Wyoming and Montana experience swarms of small quakes extending well beyond the caldera. The stress field they represent reaches across the northern Rockies. Farther west, the effects of the same mantle currents appear in the Basin and Range province, where lithospheric stretching releases tension instead of exploding. Both regions tap the same energy, but in different mechanical modes. Extension in one, uplift, and eruption in the other. That duality suggests the forces under North America are redistributing themselves, with some areas sinking or stretching while others heat and rise. Yellowstone sits at the confluence of both, a localized outlet for continental-scale processes. Despite popular imagination, scientists don't expect an imminent doomsday eruption. Modern monitoring, satellite radar, seismometer arrays, and gas flux sensors shows no signs of catastrophic pressure buildup. The Crustal system continually vents steam and minor magma intrusions, dissipating energy gradually. But the risk isn't zero, and understanding it demands tracking the links that connect Yellowstone to far larger dynamics. If the Farallon remnants shift or if mantle convection beneath the continent reorganizes, the heat supply could focus again under the caldera, accelerating melt production. In that scenario, the timing of the next large eruption may hinge as much on processes thousands of kilometers away as on local conditions. Even without a super eruption, the region remains volatile on human timescales. Steam explosions, powerful enough to carve craters, dozens of meters wide, have occurred in the last few centuries, most recently in the 198s and 200s. Ground deformation continues, and each year's cluster of small quakes outlines fluid movements that feed the geysers tourists marvel at. Those geysers themselves are pressure gauges. When intervals shorten or elongate, scientists know something has changed beneath. Viewed from space, the Yellowstone region glows faintly in thermal imagery, a patch of excess heat venting from the crustal breathing of the continent. That glow is mirrored in smaller ways across the western United States, in Nevada's hot springs, in New Mexico's Socorro uplift, even in the volcanic fields of Arizona. They're all connected fragments of the same deep circulation cell, mantle material rising beneath the thinning continent, swapping energy with descending slabs at depth. It's as if the planet is continuously stirring its interior, and the surface expressions, earthquakes, rifts, geysers, are ripples from that stirring. Yellowstone's story then is an isolated wonder, but the visible pulse of North America's ongoing restructuring. The supervolcano is simply the most dramatic manifestation of forces that also bend coastlines, sink deltas, and open rifts. Every bubble in a geyser, every sulfur hiss, is a whisper from the same engine reshaping the continent's skeleton. Beneath the illusion of a stable landscape lies a hot, moving dialogue between past and present. Ancient subduction dragging down, modern plumes bringing material back up. The balance between them decides whether this land rises to new heights or sinks beneath the sea. For now, we live in the calm between major breaths. The mantle still warms the underside of the continent. Pressure ebbs and flows, and surface life carries on atop one of the planet's most intricate geothermal systems. One day, perhaps tens of thousands of years from now, that balance may tip again. The ground will lift perceptibly, tremors will escalate, and the heat below will seek release not as steam, but as fire. On that day, Yellowstone will remind the world that the same invisible current swallowing parts of the continent can just as easily force it upward, an equilibrium written in magma destined to continue as long as Earth keeps breathing beneath North America. Reading the science, geological evidence, and modern monitoring. If Earth's deep processes sound abstract, the proof is written across the continent's surface. Every upward swell, every sinking delta, every tremor recorded by steel pins in bedrock tells us that North America is changing right now. Scientists aren't waiting on theory. They're watching the planet rewrite its own map in real time. Start with satellites. From hundreds of kilometers above, radar interferometry, known as INSAR, tracks ground motion to millimeters. Over the Gulf Coast, the data show vast depressions spreading like invisible bruises across Louisiana and Texas. Near Houston, the ground subsides at nearly 2 inches per year, where groundwater extraction empties deep aquifers and soft clay compresses. But even in places untouched by pumping, the coast continues to sink. GPS stations pinned into bedrock confirm a persistent downward drift, almost as if the entire shelf is slowly giving way under invisible weight. Comparing these points with sea level sensors reveals the harsh arithmetic. The land is dropping faster than global sea level, is rising, amplifying flood risk by double. From shoreline to seafloor, instrumentation now extends the record. Off the Louisiana coast, pressure sensors anchored to pipelines and research buoys measure vertical motion of the seabed itself. Some show subtle flexing of the crust, fractions of an inch each year, relate to sediment loading and mantle relaxation below. Those signals echo satellite gravimetry readings taken by NASA's GRACE mission, which can detect how mass shifts in Earth's gravity field. GRACE data show the Gulf region losing landmass, not just from erosion, but from deep compaction. In the simplest terms, the continent is sagging under its own sediments, and gravity keeps the score. Far to the north, other satellites record the opposite trend. Over the Canadian Shield, the crust is still rising slowly, rebounding from the weight of glaciers that melted 12,000 years ago. That contrast, uplift in the north, subsidence in the south, creates a gentle tilt that helps push coastal waters farther inland along the Gulf. It's the after effect of the Ice Age, meeting the slow pulse of mantle convection. The planet doesn't reset evenly, it balances by degrees. Deep below, geophysical imaging offers an entirely different kind of evidence, pictures made from sound. Seismic tomography, like CT scans for the Earth, uses thousands of earthquakes as probes. Sensors scattered across North America record how each tremor's waves bend, accelerate, or slow while passing through layers of rock. When those signals are assembled, they reveal three-dimensional patterns, zones of cold, dense material sinking, and regions of harder, weaker mantle rising. Over the last decade, data from the EarthScope and US Array projects have formed the clearest portrait of these hidden structures ever collected. What the images show is startling. Beneath the Midwest, plumes of high-density drips descend 100 kilometers into the mantle, the very definition of Cratonic dripping. Under the Rockies and Southwest, broad low-velocity regions betray rising warmth pushing upward. And stretching like a colossal scar beneath the western margin lies the ghost of the Farallon Plate, pieces of it still sliding, twisting, and fragmenting. In 3D models, those fossil slabs look like tattered curtains reaching from the surface to more than 600 kilometers deep. They're heavy enough to redirect the surrounding mantle flow, and that flow in turn influences everything from Cascadia's locked fault to subtle sagging in the Great Plains. To test these models, geologists paired them with surface heat flow measurements. Thousands of sensors sunk into boreholes across the United States measure the gradient between shallow crust and basement rock. The patterns line up neatly with seismic images. Higher heat where mantle material rises, lower where ancient slabs sink. Along the Rio Grande Rift, geothermal gradients more than double the continental average, affirming that upwelling continues beneath New Mexico. By contrast, in the stable core of the Canadian Craton, the gradient is low, evidence of old, thick lithosphere protecting the surface from mantle heat. Comparing these signatures over time shows that even stable crusts aren't immune. thermal profiles are gradually changing as deep convection erodes their base. Yet satellites and seismographs only hint at movement. The tangible record lies in rocks and sediments, the ground truth of Earth's long experiment. Near the Gulf, cores extracted from coastal marshes tell a layered story, peat horizons overlain by tidal muds, each transition marking a moment when land dipped abruptly below sea level. Radiocarbon dating reveals sequences of drops every few centuries, some synchronous across hundreds of miles. It's evidence not of localized settling, but of regional flexure, the lithosphere bending downward, under shifting weight or crustal thinning beneath. In New Orleans, those layers literally underpin the city. Many foundations rest atop buried forests drowned by ancient subsidence. Inland drill cores from the Mississippi embayment reveal bent and broken strata, twisted ever so slightly by slow warping of the crust. At Holocene timescales, mere thousands of years, those bends amount to inches, but stacked over millions, they become basins. Even the shape of the lower Missouri River Valley owes much to this long flexure, a sag created by mantle currents converging beneath the central United States. The evidence isn't theoretical, it's physically dug out of the ground. Meanwhile, astronomers' tools repurposed for geology, like laser ranging, now complement these clues. Using beams bounced from satellites, researchers measure the distance between fixed points across the continent with millimeter precision. Over decades, the Midwest cluster appears to drift downward relative to the Canadian shield by roughly 0.5 millimeter per year. On paper, that looks trivial. In reality, stretched over 1,000 kilometers, it equates to millions of tons of rock adjusting, infinitesimally yet steadily, under forces from deep below. Along the Pacific edge, ocean-bottom observatories continue to capture Cascadia's tense choreography. Pressure sensors flatten fluctuations into data that reveal micro-uplifts every time the fault flexes. Each of those blips, though barely a millimeter, shows the crust straining like an elastic plate nearing its limit. A similar pattern, though mirrored downward, is seen along the Gulf Shelf, where continuous GPS receivers mounted on oil platforms display uniform descent. Whether plate compression or gravitational settling, the numerical fingerprints read the same message: motion never stops. Then there's the geochemical evidence, Earth's chemical diary. Volcanic gases, groundwater isotopes, even helium seepage trace what's happening far below. In Idaho and western Montana, helium ratios indicate mantle-derived gases leaking along fractures tied to the Yellowstone plume. Thousands of miles away, coastal springs in Texas and Louisiana release gases with subtle isotopic biases suggesting connection to deeper sources, perhaps along faults linking to mantle flow channels. These signatures don't travel on their own. They're pulled up when the crust flexes or cracks. Chemically, the continent exhales the signs of its internal struggle. The newest frontier in monitoring brings artificial intelligence into the picture. Massive datasets from satellite radar, seismic sensors, and gravimetry are now too immense for manual interpretation. Machine learning algorithms trained on known deformation patterns comb through the noise, flagging anomalous movements that may indicate new zones of stress. In 2023, one such system detected coordinated micromotions across the lower Mississippi Valley, subtle wobbles in ground elevation synchronized with deep mantle flow predicted by models of dripping lithosphere. The discovery lent statistical backing to something geologists had long suspected, that the continent's interior breathes in unison with its edges. Even the oceans contribute measurements now. Autonomous submersibles in the Atlantic monitor spreading along the mid-Atlantic ridge, mapping where new seafloor forms as older crust elsewhere, like that under North America, recycles downward. While half an ocean away, changes in ridge dynamics influence pressure at subduction margins and may slightly alter the force balance under the continent. It's another reminder that tectonics is global choreography. Every plate motion sends ripples through the planetary system, echoed by sensors continents apart. Back on land, paleomagnetic surveys add yet another line of proof. As molten rocks cool, their magnetic minerals lock in the direction of Earth's field at that moment. By sampling formations of different ages, geologists can track how regions of crust have tilted or rotated. Across the western interior, those angles show progressive rotation consistent with continuing extension in the basin and range. Even the stable Great Plains reveal minor but measurable tilts eastward, fractions of a degree over millions of years, aligning with the direction of mantle flow derived from seismic and anisotropy studies. The crust itself behaves like a buoy drifting on a slow current. To ordinary citizens, this evidence can feel remote, but there are visible day-to-day clues animated by these same forces. Sinkholes forming across Florida and Texas often begin where groundwater extraction intersects subsiding clay beds. Coastal wetlands vanish not only from development, but because the ground beneath them physically lowers. In Alaska, post-glacial uplift raises former seafloor to dry land within human lifetimes, an opposite motion equally tied to mantle elasticity. Each flooded street or rising headland participates in the same planetary mechanism. What makes it today different from any earlier epoch is how completely these signals can now be observed in real time. A century ago, it took generations to notice that harbors deepened or shorelines shifted. Today, scientists track cumulative millimeters of change almost as they happen. Networks like the Plate Boundary Observatory orchestrate more than 1,000 GPS receivers transmitting second-by-second positions. Coupled with satellite constellations analyzing moisture, temperature, and gravity, they produce an evolving 4D model of the continent, latitude, longitude, altitude, and time, revealing that the land breathes like a living organism. In that data, patterns emerge. The Gulf Coast subsides fastest where ancient river sediments are thickest. The Rockies rise subtly along their central spine, buoyed by warm mantle pushing upward from the foundering Farallon remnants. The Midwest slow sag forms an ellipse that mirrors convection modeled beneath. Even subtle oscillations of microgravity correspond to water loading during floods and droughts, a coupling between atmosphere and crust. Each dataset corroborates the others, painting a coherent picture of a continent in motion from core to coast. Understanding these measurements is more than curiosity, it's survival strategy. Predicting catastrophic quakes or eruptions may remain elusive, but long-term monitoring reduces uncertainty. By mapping strain accumulation, engineers can redesign infrastructure to flex rather than fracture. City planners along the Gulf now integrate vertical land motion data into building codes. Railroads crossing the Great Plains use satellite deformation maps to anticipate where track beds might warp over decades. Even insurance markets quietly reference geodetic trends to price coastal risk. Meanwhile, scientific collaboration stretches beyond geology. Oceanographers use the same pressure records to model sea level anomalies. Climatologists correlate them with rainfall and groundwater extraction. What once seemed separate, climate change above, tectonic change below, now interlaces through shared measurement. Rising seas amplify the effect of sinking land, while sinking land worsens storm surge impacts. Satellites tracking both merge their data to reveal how intertwined they really are. Perhaps the most haunting evidence comes from ancient analogs newly uncovered. Deep cores drilled from the Atlantic shelf hold layers of marine clay deposited when past portions of North America temporarily sank below sea level during warm intervals. Chemical fingerprints within those clays mirror present-day trends of subsidence. It suggests we've been here before, continents breathing downward, seas invading, then retreating as mantle flow shifted again. The cycle plays out every few million years. Only this time, our cities happen to occupy the battleground. Every strain gauge, seismic trace, and isotope ratio converges on a single conclusion. North America isn't static. Its crust is deforming right now, slowly, unevenly, invisibly to us but perfectly clear to the instruments listening across sky, sea, and stone. Where old subducted slabs still sink, land above them sags. Where heat rises, it lifts. From the Gulf's vanishing marshes to the Rockies' imperceptible climb, from Yellowstone's breathing floor to Houston's quiet descent, the measurements align like verses of one long geological sentence. And in the subtext of that sentence lies our era's defining realization. We are witnessing a continent caught between its own opposing forces, with science providing the first exact words of translation. The tools are tuned, the signals unambiguous. The Earth's pulse is measurable, steady, and unstoppable, and its beat tells us that the swallowing has already begun. Mitigation and resilience, preparing for the inevitable. If the continent itself is shifting, sinking, and stretching in ways measured only through decades of data, then the hardest question becomes clear. How do we live on something that never stops moving? Along every one of these fault lines, Cascadia, New Madrid, the Rio Grande Rift, the Gulf, scientists and engineers are rewriting the manual for survival. The answer isn't avoiding the hazards, it's learning to live with them. Across the Pacific Northwest, entire towns have begun to rearrange their survival logic. Seaside Oregon once planned its growth near the beach. Now it moves schools to high ground. New evacuation towers rise along the coast, tall enough to stay above any plausible tsunami. Communities map vertical escape routes, stairways not to rooftops, but to safety above the floodline. The state's Department of Geology even posts signboards along highways, reminding drivers that the next megathrust quake could arrive any century, and that the first warning might be the ground itself. Beneath those warnings lies a quiet revolution in engineering. Since the late 199s, architects have borrowed lessons from Japan and Chile, countries living on. Similar plate margins to reinvent building codes for seismic flexibility. Instead of rigid frames meant to resist shaking, new structures are designed to sway. Base isolation pads made of rubber and laid separate foundations from the ground, allowing movement without collapse. Ports, fuel terminals, and bridges are being retrofitted with sliding joints that absorb displacement. Hospitals and emergency centers, often built on soft deposits, now anchor to deep pilings drilled into stable rock to prevent liquefaction. But resilience isn't only concrete and steel. It starts with data. Early warning networks spread like neural tissue across the continent, feeding real-time signals to computers trained to recognize the first tremors. Systems such as Shake Alert on the West Coast can deliver several seconds of notice before major waves arrive. Barely enough time to halt trains, shut off gas lines, or trigger automatic door releases in fire stations. Yet in those seconds, human lives are saved. The more refined the sensors become, the sooner that pulse will reach the phones in people's pockets, giving them one final heartbeat of warning before the shaking. In the Gulf South, resilience wears a different face. Here, the threat isn't sudden but slow. A persistent drowning by subsidence and sea level rise. The challenge turns from seconds to decades. Louisiana's coastal master plan, updated every 6 years, acts as a blueprint for continental triage. It combines levee upgrades with sediment diversion projects that reconnect the Mississippi River to its sinking delta. By letting the river deposit its load back into the wetlands, engineers hope to rebuild as much land as gravity takes away. It's geosurgery performed on a living coast. Cities along the Gulf integrate satellite-derived subsidence maps into zoning laws. In Houston, planners use NASA's INSAR data to decide where new pipelines can safely stretch without buckling. In Mobile and Tampa, building elevations now factor in projected sea level curves through the year 210. Insurance companies quietly recalculate premiums using those same curves, recognizing that what appears as a 100-year floodplain may, within a few decades, become annual terrain. The lessons learned there ripple northward. In the Midwest, communities perched above the silent new Madrid fault have revived awareness campaigns dormant for generations. Schools host earthquake drills for the first time since the Cold War. Engineers in Memphis retrofit bridges with flexible bearings designed to survive lateral motion unknown to local history. The region's lifelines, water mains, gas pipelines, electrical conduits are being mapped against liquefaction risk zones derived from soil cores. Just as coastal cities brace for floods, inland ones begin to prepare for ground waves. Technology pushes adaptation further underground. The U.S. Geological Survey, NOAA, and NASA have begun joint modeling that couples tectonics with hydrology. By linking satellite mass measurements with groundwater withdrawal data, scientists predict where human activity intensifies natural sinking. That feedback turns research into management. Limiting pumping in vulnerable zones can slow subsidence measured from orbit. It's one of the few instances where small choices, conserving water, redirecting wells, translate directly into measurable stability. Further west, the challenge is balancing natural hazards with energy demand. The basin and range's abundant geothermal fields promise clean power, yet every borehole drilled into that living crust must respect faults capable of near-surface movement. Regulators now require real-time microseismic monitoring at all geothermal sites. If tremor counts spike, injection volumes are throttled back. It's environmental reflex built into infrastructure, science acting as conscience. Then there's the frontier of digital modeling. Three-dimensional Earth simulators now incorporate mantle convection patterns, crustal thickness variations, and expected seismic cycles to forecast where stress migrates. The data feed into urban planning just as climate projections inform storm preparedness. Geologists once published maps that looked backward into prehistory. Now they publish probabilities looking forward. When every pixel on a regional map encodes decades of crustal motion, city design starts to resemble planetary design. Programs such as the Incorporated Research Institutions for Seismology bring portable seismometers into classrooms across the United States, letting students record tremors from half a world away. That awareness matters more than concrete sometimes, because public memory tends to fade faster than geological cycles. The last great earthquakes feel ancient. 170 Cascadia, 1811 New Madrid. But their recurrence intervals sit well within the lifetime of nations. Resilience thus depends on keeping knowledge alive between events, ensuring each generation inherits, not fear, but familiarity. For every coastline retreating and every river valley bending, preparation functions like cultural evolution. The earth changes too slowly for panic, yet too surely for complacency. What survival requires is choreography, not defiance of natural processes, but timely movement within them. The ground shifts, we adjust. The sea rises, we rebuild higher. Resilience is no longer about conquering nature but synchronizing with its tempo. North America on geological time. In human time, continents feel eternal. In Earth's time, they drift, sink, and breathe. North America's story proves that our solid ground is only the visible half of a convecting machine running since the world was molded. Beneath its forests and cities, the Farallon Plate still slides downward, mantle currents still reshape its shadow, and drips of the ancient Cratonic still fall into the deep like grains of slow sand. From the Gulf's disappearing marshes to Yellowstone's restless heat, every phenomenon we call disaster is really continuity, the latest heartbeat of a planet that never rests. The continent is not being punished. It's participating in a cycle that will outlast language, architecture, and coastlines alike. If there's meaning here, it's that fragility and persistence coexist. We adapt, measure, and rebuild because the continent itself is learning how to balance. Each levee, evacuation route, and seismic network becomes part of that adaptation, humans weaving themselves into geological time. One day the seas will reach farther inland and mountains will rise somewhere else, but for now this continent is ours to read and to respect. If you want to see how these forces continue shaping our future, watch our next exploration and subscribe to follow the planet beneath your feet still writing its story.